This is the seventh lecture on Fourier transform. Today we shall consider Fourier cosine transform. Fourier cosine transform. For even function, we have seen that the Fourier cosine transform is defined as f of x is equal to a for cosine k is equal to 2 by pi integration from 0 to infinity f of x cos of kx dx, and the inverse transformation is this is Fourier cosine transform. And for Fourier sine transform we have this is applicable for odd function, and the inverse transformation is this. This is square root of 2 upon pi this is the Fourier sine transform and cosine transform. We shall first apply the Fourier sine transform to a step function. Example 1 is a step function. So it is defined as f of x is equal to a for x in between this and 0 otherwise. So if we calculate the cosine transform, AC of k is equal to root 2, then the f of x is a, and we have cos kx dx from 0 to a. This definition where fx is equal to a for x being limit 0 to a and 2 by pi a. If we integrate it, we will have in the denominator k, and in the numerator it will be sine kx, and within 0 limit it is 0, so it is sine ka. Similarly, this is now you see the graphical representation, which is very important. The function is like this. This is its function, the Fourier transform. The Fourier cosine transform is you see it is sine ka by ka. So if we put it a and at k is equal to 0, it is this much, and then oscillates, damped oscillation. This value is the peak value. And if we come to this, at k is equal to 0, at k, firstly, the numerator is always positive because cos k is between plus minus 1. So numerator is a non-negative, essentially non-negative. So the sign of AS is determined by the sign of K. So on the right hand side, on the positive half it is positive, and on the negative half it's the AS is negative. Secondly, this has a singularity at K is equal to 0. So at K is equal to 0, it is 0 by 0 form. At K is equal to 0, it is of the form 0 by 0. So we define it as the numerator function and the denominator function as we did earlier. So n of k is equal to 1 minus cos ka, and its derivative is a sine ka. We are differentiating about with respect to k, and denominator function is k, so d prime is equal to 1. So this is now become this form. This is now a sine k a by 1, which tends to 0 as k tends to 0. So this is an important finding. So we write the now as the second example, we consider exponential function. F of x is equal to a e to the power minus alpha x, where alpha is a positive quantity. So we first calculate cosine transform. In the earlier class, we have also evaluated this function, and on simplification, or if we carry out the exact calculation, it becomes 2 by pi a times e to the power alpha by alpha square plus k square. This is the form of a of k. If we want to find out the function itself, if we use inverse transformation, this is 2 upon pi ac of k cos kx dx from 0 to infinity. Now if we write this value, it is a e to the power minus alpha x, the function, as we know. And in this case, this is 2 by pi times a, integration over, and alpha is out, so cos kx this gives us the integration 0 to infinity cos kx dk alpha square plus k square is equal to pi by 2 alpha. An important result, if we integrate it with respect to x, then in terms of x the result is cos kx dx alpha square plus x square from 0 to infinity is equal to pi by 2 alpha. It is an important relation, and we will require it, so we preserve it as 0 to infinity cos kx alpha square plus x square dx is equal to pi by 2 alpha. And if we find the sine transform, the sine transform is thus: as of k is equal to e to the power minus alpha x sine of kx dx from 0 to infinity. And if we use our standard result, it is 2 by pi a k upon alpha square plus k square. The inverse transformation gives you this is a e to the power minus alpha x, and this is 2 upon pi, because another 2 upon pi comes from here, and then integration k sine kx alpha square plus k square dk integrated from 0 to infinity, which gives us the result that two by pi. And if we write it in terms of x, the result is 0 to infinity x sine kx alpha square plus x square dx is equal to pi by 2 e to the power minus alpha x. Oh, I have missed e to the power alpha x here. Here is also I have missed e to the power minus alpha x, because the alpha x was there, and it will go and it will be e to the power minus alpha x. If we put alpha is equal to 0, one important conclusion of this result is that if we put alpha is equal to 0, then 0 to infinity sine kx by x dx is equal to simply pi by 2. This is another important result. Now come to the graphs of this function. The function itself is an exponential function. This is a value. If we consider the cos expansion, this is there. AC of k, and this is a function of k. You see that as k increases, this value, this functional value decreases as 1 by k square, so it is a fast jump, and this value is a by alpha, a by alpha. And if we plot the sine transform, this sine transform, I have a s of k, I have erased it. It is one thing, that it is at k is equal to 0, it is 0, and for right hand side it is positive and left hand side it is negative. So the graph is like this. You note that this function asymptotically behaves as k tends to infinity behaves as alpha by k square, which has a faster fall, and this function asymptotically behaves as k tends to infinity 1 upon k, so it has a long tail. Now come to the third example that I am going to consider. It is a function sine x by 1 by x. The function is 1 by x, and we are going to calculate its sine transform. This is the third example. F of x is equal to 1 by x. Its Fourier sine transform of 1 by x is equal to 2 by pi sine kx by x integrated from 0 to infinity dx. If we use this result, the integration is straightforward. So it is a constant. So the functional graph is this is x, this is f of x is equal to 1 by x, and the Fourier transform, sine transform is a constant. Now come to the fourth example. As the fourth example, we consider the function Laurentian function. This function is commonly known as Laurentian function. F of x is equal to a alpha square plus x square, and we want to calculate its cosine transform. And the range is from 0 to infinity, so it is 2 upon pi, a will come out, so cosine transform cos kx alpha square plus x square dx from 0 to infinity. We use this relation to evaluate the integration. It is pi by 2 alpha e to the power minus alpha k. So on simplification, it is a by alpha alpha k. The graph of the function is like this. It is a symmetric graph, and for this part it decreases exponentially. And this value is this much. This is a peak value. As the fifth example, we consider a modification of this function, and we'll find out the corresponding cosine sine transform. Note that this function was a even function, so we write f of x is equal to ax alpha square plus x square, and its Fourier sine transform is A will come out x sine kx alpha square x square dx from 0 to infinity. For this we use the second relation, this one. The result is two by pi a, and it is pi by 2 e to the power minus alpha k. So it is 2 it goes off exponential. If we plot this function, symmetric graph, and it has an exponential dump. This peak value is this. Now come to the another interesting example, cos function defined over a limited period. In earlier case, when we have discussed about Fourier transform, we have examined cos function integrated over defined over a finite interval. Here we use f of x is equal to cos of alpha x with x less than a greater than 0, and it is 0 otherwise. So this is being a even function, we calculate Fourier sine transform this we write to, we have used a 2 here and adjusted this 2 with this, so we get it is cos so on integration it becomes first term, in the denominator it will be sine k minus alpha a by k minus alpha a. This a is multiplied, which is being adjusted over here, plus k plus alpha a this graph. If we plot this graph, first we plot this plot. F of x is equal to cos of alpha x. Say it is, and then 0, and the corresponding Fourier cosine transform will consist of two peaks. Both are erect. One is k is equal to alpha, and this is k is equal to minus alpha. Both the peaks are erect peaks, and this curve will have an and similarly if we use sine here, then these both the terms will be sine, and I just indicate what will be the change. If it is be sine, then the changes are that this is sine, this is also sine, this symbol will be minus this by, so it will consist of this peak will be on the negative side. This peak will be on the negative side and this peak will be on the positive side. Now I come to, this is the seventh example. For seventh example, this is right 7 for sine. Now come to the eighth example of this lot. Eighth example is a Gaussian function. We have seen earlier that the Fourier transform of a Gaussian is a Gaussian. So let us see what happens for a Gaussian function. Its Fourier transform cosine. We define a subsidiary quantity I is equal to this much. We differentiate I with respect to k. So what we will get? This is minus k, minus x. So it is minus x e to the power minus alpha x square sine of kx dx. Now if we take the differential of this, d of e to the power minus alpha x square, it is equal to minus 2 alpha x e to the power minus alpha x square. Minus x alpha x is there, so we can write minus x e to the power minus alpha x square is equal to 1 upon 2 alpha d of x e to the power minus alpha x square. So this is plus 1 upon 2 alpha has to be adjusted. We integrate by parts. So this is first term. Then if we, this is I3, I. So the result is, and you have to put it within limits. At x is equal to 0, it is 0 due to the sine factor, and at x is equal to infinity, it is 0 for this factor. So the result is minus k by 2 alpha I3. So you know, so I. So if we integrate this, this gives you I of k is equal to some constant c times e to the power minus k square by 4 alpha. Now we need yet to determine the constant c. So we write I at k is equal to 0 is equal to c is equal to, now we come to the definition with this. It is 0 to infinity e to the power minus alpha x square dx. If we use the property, then we find that it is half. Using gamma function, it is half times pi by alpha. So combining all this, we get the Fourier transform of Gaussian function as a again the Fourier transform of a Gaussian is a Gaussian. If we want to find out the sine transform, as it is an even function, we cannot find the sine transform of it. So we are to make the function odd first. So to make the function odd, we write thus. And if we find out the Fourier transform of it, we will find that it is of the form e to the power minus k square by 4 alpha, and the numerical factor is a upon 2 pi to the power 3 by 2. It's an homework, left-hand homework, and you use the function I just defined beforehand. To conclude this discussion, we shall use the Parseval relation for Fourier sine and cosine transform to evaluate specific integrals or definite integrals. So this is the last example on Fourier series, and from the next class we shall go to Frobenius method, Parseval relation. We consider two functions, f of x and g of x dx is equal to, it says that it is a of k g b of k star dk. This is Parseval relation in general. And the integration extends from minus infinity to plus infinity. For Fourier sine and cosine transform, this simplifies to 0 to cosine or sine, as the case may be. This is the Parseval theorem. We consider f of x is equal to e to the power minus alpha x. So AC, its transform is we have evaluated it earlier. And its sine transform is similarly, we will consider function g of x is equal to e to the power beta x. Its cosine transform is and its sine transform is so the plan is this. Now since beta is a real function and g is a real function, g star is g. So if we apply this theorem for Fourier cosine transform. Then the left hand side. The left hand side is e to the power minus alpha x e to the power minus beta x dx from 0 to infinity. On the right hand side, cosine function. So this will be the product of these two. So it will be 2 by pi, and alpha beta will go out of integration. Then it is the integration of this plus this. Alpha square plus k square beta square plus k square dk from 0 to infinity. This part is simply 1 upon alpha plus beta is gamma function. So we get 0 to infinity alpha square k square beta square k square dk from 0 to infinity. It is pi upon 2 alpha beta alpha plus beta. If we look at as integration, then we can as well write it. Forget about Fourier transform or anything. We write it is x this is the relation. If we use the cosine transform, then there will be no alpha beta product term and it will be k square. So for Fourier sine transform, the result will be integration from 0 to infinity alpha square x square beta square x square dx from 0 to infinity. The right hand side is pi by 2 alpha plus beta. These are the important integrals, and complicated integrals have been evaluated using the Parseval theorem. That's all about Fourier transform.